Jnanam Paramam Dheyam. Knowledge is supreme.
So, let us look at some examples for that. Let us look at I have got 6 vectors v1, v2, v3, v4, v5 and v6. What is the how many components are there? Each is a vector in R4. So, there are 6 vectors in R4, number of vectors is more than right R4 n dimension. So, these will be linearly dependent set straight away, it is a linearly dependent set, right. I want to find out of all this which ones are linearly independent out of the 6, right. It is a dependent set. So, probably one of them I can throw, maybe 2 of them I can throw out or remove 3 of them, I do not know how many. I want to find out which are the vectors which put together will give me a linearly independent set, and that should generate the same vector space as all of them. All these 6 generate a space, vector space, the linear span, right. I want a basis for that vector space, right. So, what will be the basis? It should be a linearly independent subset of the generators, one. And what is the second thing? It should be linearly independent and generator, 2 things. It should generate everything and it should be linearly independent. So, I want a subset of these 6 vectors which is a linearly independent set, and all 6 of them can be represented, each one of them can be represented as a linear combination of those whichever I choose. So, what is the process of doing that? I am going to describe that. Okay. So, let us look at. So, these are 6 vectors each having 4 components. So, it is a linearly dependent set, obvious, right. So, what we want to do? We want to find a maximal linearly independent subset, right. We find a part of it which is linearly independent and a maximal, say 3 of them I find and 4 of them will not be linearly independent, then that will form a basis, right. Definition of basis, either it should be a maximal linearly independent set or a linearly independent set which generates, either of them is okay, or it should be minimal set of generators. These 3, either of the conditions I can use criteria. So, let us look at. So, what is the process? I take these vectors v1, v2, v3, v4, v5, v6 and make them as the column vectors. So, the algorithm is the following. I will put these vectors as the column vectors and form a matrix A, right. Now, I want to find out which one are linearly independent. So, I will reduce that matrix to row echelon form. I will reduce the matrix to row echelon form and I will look where the pivots are coming, right. Wherever pivot is coming, the corresponding vector I should pick up from the original one, the column vector, corresponding one I should pick up. That collection should give me a basis for the column space, right. So, from that theorem this should be the algorithm. So, let us do that. So, let us form that matrix. So, this is the matrix A by putting, right, each column is that vector. Okay. So, the first one is 1 1 3 and so on. So, that is what we have done 1 1 1 3 and so on. So, all these 6 are put as columns. So, I get a matrix. What is the order of the matrix? There are 4 rows and 6 columns, 4 cross 6. I want to reduce it to row echelon form. So, what I will do? I know the process of doing it, right. I will look at the first column, see where the non-zero entry is coming, make everything below 0 and so on, go on doing it. By elementary row operations, that is interchange is allowed, multiplication by a non-zero scalar is allowed and addition of 2 rows is allowed. So, once I do that, we will not spend time on doing that. So, this is what I get. This is what. So, this is it in the row echelon form? The first non-zero entry in the first row is coming at 1, everything below is 0, right. The next in the second row, the first non-zero entry is coming at the third place, everything else below that is equal to 0, right. In fact, above that also is 0. So, this is what is the reduced row echelon form, right. In that column everything is 0. The next pivot in the third one is coming at this place, right, 1, this is 1, 2, 3, 4 and 5, the fifth place, and everything else is 0. So, that these are the only pivots, right, because in the next row everything is 0. So, this matrix you do not have to bring it in the reduced row echelon form, row echelon form is good enough. What we want to know is where are the pivots coming, right. So, here the pivot comes in the first place, P1 is 1, P2 is 3 and P3 is 5. So, we will pick up the corresponding vectors in the original collection V1, V3 and V5, right. So, anyway here it is a rank is equal to 3, total number is 6. So, let us find a basis of the column space. So, I pick up V1, V3 and V5, those are the pivotal vectors in the original one. So, here is V1 tilde, this is for the reduced form, these are pivotal columns in actual reduced form. The original one will be from V1 tilde corresponding V1, V3 and V5, these are the original ones we pick up, clear. Reduced row echelon form or row echelon form, look at the pivotal columns, corresponding columns from A you pick up, the original ones. Now, the claim is these three vectors should be linearly independent, right, and should span everything. I want to check that also, right, theorem says it should be so. So, let us try to verify that by this example. Okay. So, I want to verify is a linearly independent subset and in fact spans all the remaining ones. So, let us check. First of all, how do I check linear independence of the 3, right. So, let us take alpha times the first vector, alpha to beta times the second one and gamma times the third one, right. I should not be putting okay. This bracket is redundant, actually it is a linear combination equal to 0, right. In the mathematical notation this bracket should not be there. Okay. If I want, I should put on the right hand side also a bracket, it will be 0, left hand side is a set, right hand side is a vector, right. So, mathematically typo here, either I should remove these brackets. So, basically what you are saying, look at the linear combination of the three vectors, alpha times the first one plus beta times the second one and gamma times the third one equal to 0. What will give me? Alpha into 1 plus beta into 0 plus gamma into 1. So, first equation is alpha plus gamma is equal to 0. So, write down the equations, this system of equations now, right. So, these are four system of equations, alpha, beta and gamma. Find out solutions of this, right. You can check, see alpha plus gamma equal to 0 will give you this is equal to minus, put the value here and solve it. If you solve these things, it will give you that alpha is equal to 0, it could be gamma equal to 0, all three are 0. That means, we are checking by the very definition, if a linear combination of vectors is 0, then each one of them is equal to 0 by looking at the corresponding system of equations. So, these are linearly independent, that is verified. Next, what should I do? Check that all 6 are linear combination of these 3, but these 3 are themselves anyway linear combination of themselves. So, remaining ones, right, are linear combinations. So, let us look at that. So, this is V2, V2 was 2, 2, 2, 6, this is 2 times V1. Okay. Next one is V4, V4 is that is minus 3 times 1, 1, 1, 1, 3, right, minus 3 times V1. And how did I find out this, that this is a linear combination? How will you do it? What we are doing is, I want to write V6 as a linear combination of the 3 vectors. So, I will take alpha times this vector plus beta times this plus gamma times this equal to this vector now. So, that system of equations I will have to solve, that system alpha beta gamma equal to constant, I will have to solve that, I will get the vectors alpha beta and so I solved that, okay, and I got 2 minus 1 and now I can check whether this sum comes out actually equal to this linear combination is equal to this or not, right. So, that means the vectors V2, V4 and V6 which were not selected as part of the pivotal columns are expressed as linear combinations of the pivotal columns of A itself. So, all the vectors V1, V2, V6 are linear combinations of those 3, right, and those 3 were linearly independent. That means, those 3 form a basis for the linear span of the columns, right. So, that is how you find the columns. So, linear span of V1, V2, V1, V3, V5 is same as linear span of all the 6 vectors, right, and each one of them we wrote as a column. So, this linear span, so what is this V1, V2, V5? They give me a basis for the column space of the matrix A, right, because we wrote everything as the columns. And in the row echelon form, whichever were pivotal columns, the corresponding ones should give me the basis, and we have verified that. Okay, right. So, this is I put the as a algorithm. Suppose you are given vectors V1, V2, V3, Vn, a given set of vectors, to extract a maximal linearly independent subset out of it, right, that is the aim. Given a set of vectors, I want to extract a maximal linearly independent subset out of the given set. I want to find a subset which is linearly independent at the largest subset. So, the algorithm is consider M cross N matrix by writing these as a column vectors. So, given vectors, write them as the column vectors, right. Once you written them column vectors, reduce them to the that matrix to the reduced row echelon form or row echelon form, and look at the pivots P1, P2 and PR. R is the rank. So, there are pivotal columns. Pick up those columns VP1, VP2 and VPR. Those columns is the right, that collection is the maximum linearly independent subset, right, and this we have verified in one example, and this can be put on a computer. This can be put on a computer, right, because matrices can be put on a computer. All computation of changing, reducing to row echelon form is pre-multiplication by matrices. So, a machine can do that job, okay, but in the exam will be the machine doing, okay, we will have to do it ourselves, right. So, this is one algorithm. Now, another possibility is that you are given a set of vectors, you are not interested in knowing which one of them are linearly independent, but you just want to find a basis for the linear span of those vectors. You want to find some basis. Here what we are doing, given the set of vectors, we are finding among the set of vectors as a basis, but sometimes you are not interested in finding basis from the given set, you just want to find a basis. So, let us look at the algorithm for that. So, that algorithm is, you are given vectors V1, V2, Vn, right, you look at the linear span, I want to find some basis of it, right. So, what I do, write the matrix A. Now, instead of writing these as the column vectors, write them as the row vectors. So, form a matrix. So, why is this transpose? Because V1 normally is taken as a column, I want to write it as a row vector. So, form a new matrix A whose first row is the vector V1 written as a row vector, second V2 written as a row vector. So, write these as row vectors, you will get a matrix A, right, reduce it to row echelon form, and look at the non-zero rows. What is the property of the non-zero rows? They are linearly independent and give you the row space, right. Row space is same as the space spanned by all the vectors. So, if you want to find just basis of the linear span of vectors, finite number of them, write them as the row vectors, reduce it to row echelon form and pick up the top, right. Pick up the rows in the row echelon form, not the original one. Here you pick up the ones in the row echelon form, they will be linearly independent and will give you a basis, okay. So, let us look at this example. I have got 3 vectors V1, V2 and V3 in R2, right. There are 3 vectors in R2. So, obviously, they are linearly dependent set. So, if I take the span of them, right, that should have less than number of elements than 2, right, less than or equal to 2, any basis of the span, that is S, span of S. So, linear span of this set S can have at the most 2 vectors, right, not all 3. I want to find some 2 vectors which will give me the span of S. So, what I do, as I said, let us write that matrix. So, what is the matrix? A, what is the first vector? 2 minus 4. So, instead of writing as a row, I am writing it as a column, I am writing it as a row. So, 2 4, right, our general convention is writing as a column vector, but for this algorithm we write this as 2 4 as 2 minus 4 as the row. The next one is 1 minus 2, I have missed here minus 2 here, right, typo, and next one is minus 1 and 6. So, write these vectors as the row vectors, reduce it, when you reduce it you get reduced form is this. So, there are only 2 rows which are non-zero. So, what should be the basis? The vector 2 minus 4 and 0 comma 4. So, these two should give you the linear span. So, the two methods both require reducing the matrix to row equivalent form. When you write as columns, the pivotal columns picked up from the original one are linearly independent. When you write them as the row vectors, then the non-zero rows in the row equivalent form are linearly independent. In the first one, the advantage is you are getting a subset which is linearly independent, right. In this form, you are only getting a some basis, it is not the original ones, right, but the span of the original set of vectors, you are finding a basis for that, that is all. So, depending on what you want to do, whether you want to find among the given ones a basis or you just want to find a basis, you write it as a row or the vector as row or column, but the process will again involve reducing it to row equivalent form, that is crucial, without that you can do nothing. So, all along till now what we have done is we have tried to reduce everything to computation to row equivalent form or reduce row equivalent form, right. The key lies in that, you should be competent in that, right. So, that part I am leaving for you to check. That means what? I should be able, using these two, I should be able to write all these 3 vectors as linear combinations. So, solving 3 sets of equations, right, you have to solve that. So, do that for the practice.